your day one notes over verifying trigonometric identities. An identity is true for all values of variables for which a statement is defined. So for example, if I have something like 2x minus 4 and I factor out a 2, I'm left with x minus 2. That's an identity. What's on the left side of the equal sign is the same thing as what's on the right side of the equal sign for any value that I plug in for x. If I plug in 1 for x, what's over here is the same thing as what's over here on this side of the equal sign. Today we're going to be talking about trigonometric identities, and we're going to walk through the fundamental trigonometric identities, and I'm going to show you how they're derived from the trig functions, the unit circle, and the Pythagorean theorem. First, let's talk about the reciprocal identities. These are your basic identities: cosecant x, secant x, and cotangent x. First, we talked about trigonometric ratios, and you found that, for example, sine of theta would be the ratio of the y value to the radius, or r. And in the unit circle, r has a value of 1 unit, the unit circle. So sine theta was just the value of y. Cosecant, and we'll go back and we'll do x, because when we have cosecant x, you'll see it interchange. Cosecant theta, cosecant x. A lot of times it's just when is it in degree measure and when is it in radian measure. Typically, if there's a variable x or y or something like that, it's in radian measure. So cosecant x, that's a reciprocal of sine x. So 1 over sine x. When we talked about trigonometric ratios, cosecant theta, we flipped it. It was the value of r over y, right? It's the reciprocal. We flip it. Secant x is the reciprocal of cosine, 1 over cosine x. Cotangent x is the reciprocal of tangent x. So it's 1 over tangent x. So that means, like tangent theta, the ratio was y over x. For cotangent, the ratio is x over y. Okay, so it's just flipped. The ratios are flipped, and we can show that as identities using those trigonometric functions. Let's move on to the next set of identities, the tangent and cotangent identities. And I just covered that a little bit, but tangent theta, which I could have had tangent x there, but tangent theta is sine theta over cosine theta, y over x. Cotangent is the reciprocal of that, so cosine theta over sine theta. And again, you can write x, you can write theta. It's just know that it's sine over cosine for tangent, and it's cosine over sine for cotangent. And if you want to write y over x over here and then x over y, you can do that as well. Now let's get into our Pythagorean identities. And I've got a little basic unit circle drawn for you here because I want to show you how the first Pythagorean identity is derived. So in this unit circle, we know that the radius has a value of 1. We know that the sine is the y value. So sine x is the distance over here, the y distance, and the cosine is your x value. It's the distance of the horizontal axis. Okay, so I know that the Pythagorean theorem states that a squared, I know that it states that a squared plus b squared equals c squared. Meaning if I square the legs of the right triangle and add them together, I will get the square of the radius. This means if I take sine x and I square it, and I can write that just like this, sine squared x, and I add it to cosine x squared, which is cosine squared x, that's how I write that, equals the hypotenuse squared, which 1 squared is just 1. And this is your first Pythagorean identity, and that is how it's derived. Sine x squared plus cosine x squared equals 1. It's just something that you need to memorize. To find the second property, we're going to divide everything by cosine squared. Okay, so cosine squared. Let me see if I can, I hope that doesn't show up down there, but if it does, sorry about that. I'm going to divide everything by cosine squared. So let's see what happens when we do that. I have sine x squared, or sine squared x, sorry, plus cosine squared x equals 1. And I'm going to divide everything by cosine squared. What I do to one side, I need to do to the other side. And now I get sine squared x over cosine squared x plus cosine squared x over cosine squared x equals 1 over cosine squared x. And I know to do this using basic algebra, right? When I divide everything by cosine squared x, every single term gets divided by cosine squared. Sine x gets divided by cosine squared, and cosine squared x gets divided by cosine squared x. So what happens when we do this? Well, we know, and I'm going to go back up here, that the ratio for sine over cosine is tangent. So sine squared over cosine squared is tangent squared. Plus cosine squared over cosine squared, well, anything divided by itself is 1 equals, and then 1 over cosine squared, let's go back up to our basic identities. 1 over cosine is secant x. Do you see this right here? Which means 1 over cosine squared is going to be secant squared. And I'm going to write that just like this, secant squared x. And that's our second Pythagorean identity. Tangent squared x plus 1 equals secant squared x. What's on the left, and what does that mean? What's on the left side of the equal sign equals what's on the right side of the equal sign for any variable that I plug in, or any value that I plug in for the variable. To find the third property, we're going to divide everything by sine squared. So let's see what happens when we do that. We're going to take our basic Pythagorean identity, which we found using that unit circle, and we're going to divide everything by sine squared. And we're going to do what we just did with cosine squared, which means every term gets divided by sine squared. So sine squared x divided by sine squared x plus cosine squared x divided by sine squared x equals 1 over sine squared x. Now let's go back up here and see if we can replace some of these with, some of our other identities. Well, sine squared divided by sine squared is 1 plus cosine squared divided by sine squared. Well, if I go back up here to my tangent and cotangent identities, cosine over sine is cotangent, which means cosine squared over sine squared is cotangent squared. 1 over sine squared. Okay, let's go back up here to our reciprocal identities. 1 over sine is cosecant, which means 1 over sine squared is cosecant squared. So cosecant squared x, and that is our third Pythagorean identity. And now let's get into our last of the fundamental trigonometric identities, which we're not really going to be using these today, but they're important to know. And eventually, especially when you get into like pre-calculus, you need to memorize all of these. So sine negative x, that equals negative sine x. And when I know this, what I can do is I can just rewrite expressions in this manner. If I have a negative angle measure, I can rewrite it and put the negative in front of sine. Cosine negative x, that's the same thing as just cosine x. Tangent negative x is the same thing as negative tangent x. So let's move on to verifying trigonometric identities. What we're going to be doing here can be very confusing and frustrating for students at first. However, I promise the more practice you get with this, the more you will love it. especially when when you're verifying trig identities or solving trig equations or anything like that. It takes up a whole page to do it. I love it. It's so fun. But it does take a little bit of time and can be a little bit frustrating at first. So what we're going to do is use these trigonometric identities that we just went over to verify other trigonometric identities. To do this, you're going to change one side of the equation until it's the same as the other side. And I'm going to go through some helpful tips that you can use when we're verifying trig identities. The first thing is we're going to try to rewrite everything in terms of sine and cosine when possible. It's not always possible, but we're going to try to do that. And it's important that all you're going to be doing is rewriting functions differently. And you're going to try to set yourself up when you rewrite it to use a trigonometric identity. So you're going to be referring back to the previous table where we went through all of those fundamental trigonometric identities. You're going to have to keep that out and refer to it as you're working through all of these examples and problems. The next thing, you can rewrite both sides, but we're going to start with the complicated side first. So the first thing we're going to do is just practice simplifying each trigonometric expression. So I have cosine x times tangent x. So cosine x, tangent x. Well, let's rewrite this. Cosine x is just cosine x over 1. And tangent x, and I'm multiplying here, I'm going to put a little dot there. Tangent x, how would I write that? How could I write that in terms of sine and cosine? It is sine x over cosine x. If tangent x equals sine x over cosine x, anywhere I see tangent x, I can replace it with sine x over cosine x. We're using basic substitution. So now I've rewritten this expression in terms of sine and cosine, and we're multiplying, so let's multiply. Well, I can cross-simplify or pre-simplify, whatever you want to call it. I don't think there's like an actual term. But simplify it before you multiply, and when you do that, you get sine x over 1, which is just sine x. We've simplified it. Let's move on to number 2. I have 3 trig functions here. Secant x times tangent x times cosecant x. So using that table, go back to it. Secant x, how can I rewrite that? It's 1 over cosine x. Times tangent x, how could I rewrite that in terms of sine and cosine? That's sine x over cosine x. Times, and then cosecant x, how could I rewrite that in terms of sine and cosine? That's 1 over sine x. So now I've rewritten this expression in terms of sine and cosine because I was able to, and now we're going to simplify. Let's see, what can I do here? I've got sine x and sine x that I can simplify there, and I can do that because I'm multiplying, and that's why I can simplify like that. You can't do that when you're adding or subtracting. And that's all I can do. And now we multiply the top. 1 times 1 is 1. Cosine x times cosine x is cosine squared x. So let's move on to our last one where we're simplifying. Cosine squared theta times secant squared theta minus 1. And you might be wondering, why is there a theta there and not an x? Well, there could be a y there. There could be an n there. There could be any variable there. It just means, there's an unknown degree measure or radian measure that we could plug in there. So for number 3, secant squared theta minus 1. Well, that Pythagorean identity that has secant squared in it looks like this. Tangent squared x, and I wrote an x here, but you could write a theta, plus 1 equals secant squared. Could I rearrange this? Let me see. Could I subtract 1 from both sides to get tangent squared x equals secant squared x minus 1? I could. So secant squared x minus 1 is tangent squared x. So secant squared theta minus 1 is the same thing as tangent squared x. So what I'm going to do is I'm going to rewrite this cosine squared theta times tangent squared theta. Because I know tangent squared theta is the same thing as secant squared theta minus 1. So I'm just rewriting it. Now tangent squared theta, can I write that in terms of sine and cosine? I can. I can write it as a fraction. So there's cosine squared theta. It's cosine squared theta over 1 times tangent squared theta. How would I rewrite that in terms of sine and cosine? That's sine squared theta over cosine squared theta. So tangent is sine over cosine. Tangent squared is sine squared over cosine squared. Now let's do this. What do we get when we do this? Well, can I simplify? I can cross out the cosine squared, and I'm left with sine squared theta over 1, which is just sine squared theta. And we've simplified it. So now let's move on to the examples where we're actually verifying each equation using the trig identities. So up top, what we just did in examples 1 through 3 was we simplified expressions. We're going to be doing that in these equations, and sometimes you might have to simplify the expressions on both sides of the equal sign. Let's start with example number 4. In example number 4, we have sine x times tangent x plus cosine x equals secant x. Where's the complicated side? It's on the left. Let's start with that first. So I know tangent x, I know I'm going to have a fraction, right? Because I know at this point, maybe, you might know that tangent x is sine x over cosine x. So I know there's a fraction there. So what I'm going to first do is I'm going to rewrite this sine x as sine x over 1 times tangent x. Well, what is that? That's sine x over cosine x plus, and then we have cosine x over here. Well, that's cosine x over 1 equals secant x. Could I rewrite that in terms of sine and cosine? Secant x is the reciprocal of cosine, so I can rewrite that as 1 over cosine. Okay, now there's a bunch of things going on here. Okay, there's a bunch of things going on here. So I'm going to kind of combine steps 2 and 3 in the same step. The first thing I'm going to do is multiply these two fractions together. Sine x times sine x is sine squared. 1 times cosine x is cosine x. So I just multiplied fractions, which you just multiply across. Plus, now I have cosine x over 1. But in this case, I'm going to be adding fractions. And what's really important when you're adding fractions? Get a common denominator, then add your numerators. Okay, so I need a common denominator. That common denominator needs to be cosine x. So I need to multiply 1 times cosine x to have that denominator of cosine. What I do to the bottom, I've got to do to the top. As long as what you do to the bottom, you do to the top, then you're not changing the value of that term. So cosine x, now we are changing this to cosine x times cosine x, which is cosine squared, over, and now we've got cosine x in the denominator, equals 1 over cosine x. Now let's see. Sine x squared plus sine x squared, why don't you pause the video and see if you can find what this, how we could rewrite that, that numerator. And if you want, I'll write it like this: sine squared x plus cosine squared x over cosine x equals 1 over cosine x. Could I rewrite it like that? Well, sure, right? If I've got a common denominator, now I can add my numerators, keep the denominator. So now let's rewrite this numerator. How can I rewrite that numerator? Well, that basic Pythagorean identity says sine squared x plus cosine squared x equals, this is a Pythagorean identity, 1. So I can rewrite that as 1 over cosine x, and that equals 1 over cosine x, and we've just done it. So what's kind of difficult about this is it's kind of like a proof in geometry, right? It's not necessarily your end result that your teacher or your professor or whoever is looking for. It's all of this work in here. You've got to work through the process and get through the logic behind everything. So let's move on to number 5. In example number 5, we have secant squared x minus 1 over secant squared x, and that equals sine squared x. Okay, well, let's see. Secant squared x minus 1. Whenever I see a minus 1 or a plus 1 or something like that, I immediately go to my Pythagorean identities. This is a Pythagorean identity. When you look at your table, it doesn't at first just jump out at you like it's a Pythagorean identity, because your identity looks like this. Tangent squared x plus 1 equals secant squared x. But I can rearrange it by subtracting 1 from both sides, so I get tangent squared x equals secant squared x minus 1. So I can rewrite it. So anytime I see a minus 1 or a plus 1, go to the Pythagorean identities. See if you can rearrange them to make it look like that so that you can rewrite it. And in this case, I can. Secant squared x minus 1 is the same thing as tangent squared x. Now this is clearly my most difficult side over here. Secant squared x, I'm going to go ahead and rewrite it in terms of sine and cosine. How could I rewrite secant squared x? It's the reciprocal of cosine, so secant x is 1 over cosine. Secant squared x is 1 over cosine squared x equals sine squared x. So here's just like your complex fraction, right? I've got a fraction in my denominator. So we just want to make sure that we write everything correctly. What I'm first going to do is now I'm going to take this tangent squared x and I'm going to rewrite it in terms of sine and cosine. How could I write tangent squared x in terms of sine and cosine? Sine x over cosine x, so it's sine squared x over cosine squared x, and then we're going to be dividing by, I just kind of put like a bigger line there just to, I don't know, over 1 over cosine squared x equals sine squared x. And now, how do we divide fractions? Keep, change, flip. So I'm going to take what's in my numerator, which is sine squared x over cosine squared x. Instead of divide, I'm going to multiply. And instead of 1 over cosine squared x, I'm going to write cosine squared x over 1. And we're just showing this process step by step. And I'm changing colors with each step so you can really see. Green is step 1, the blue is step 2, the pink is step 3, and now I'm moving on to purple, step 4. So when I'm multiplying fractions, it's really important that you're really good with your basic algebra with these trig identities, and your like adding and multiplying and dividing fractions, you know, just your basic algebra rules. How do I do this? So in this, I can simplify, pre-simplify the cosine squared x, and when I multiply across, I'm left with sine squared x over 1, which is just sine squared x, and that equals sine squared x. Boom, we've proven it. We have verified it. So make sure, what I want to say with this one right here, that when you're dealing with fractions, when you're adding with fractions, get a common denominator. When adding fractions, get a common denominator. Okay? Let's move on to examples 6 through 9. And I'm going to try to go a little bit faster as I'm going through all this, but I'm trying to go fairly slow because I know it can be confusing, especially when you're just not like super good with all of your identities yet, okay? So if you need to pause the video to refer to your table, you know, the first one that we just went through, which if you don't have these notes, I encourage you to like maybe take a picture of it or something that you can just look at as you're working through this. So number 6, secant x minus cosine x equals sine x times tangent x. Let's prove this. Let's verify this. So the first thing I'm going to do is rewrite secant x in terms of cosine. It's the reciprocal of cosine, so I'm going to write 1 over cosine. Minus cosine x, I'm going to write that over 1, because I've already got a fraction on the left. Let's go ahead and just rewrite it as a fraction on the right. Equals, I know tangent x, I'm going to write it as sine over cosine, so I'm going to go ahead and put sine x over 1 times, and I'm going to rewrite tangent x as sine x over cosine x. Let's move on to our next step. When I'm adding or subtracting fractions, get a common denominator. What does the common denominator need to be up here? It needs to be cosine. Well, I don't need to change that left fraction, but the one on the right here, I need to multiply this denominator by cosine in order to get that denominator to be the same. What I do the bottom, I need to do the top. And now I get, and I'm going to kind of do this all in one step. Now I've got a common denominator of cosine. So I'm going to get 1 minus cosine squared, because that's what cosine x times cosine x is, over cosine x equals, and now we're going to go ahead and multiply these fractions. Multiply the top, multiply the bottom. Sine x times sine x equals sine squared x over cosine x. And now you may recall that this is and anytime I see 1 minus, minus 1, something like that, I think, is it a Pythagorean identity? So let's go down here. I know the Pythagorean identity is sine squared x plus cosine squared x equals 1. Could I rearrange this to get, let's see, I could subtract cosine squared x from both sides, and I would get sine squared x equals 1 minus cosine squared x. Okay, that's a Pythagorean identity. It doesn't always work out. You have to be very careful, okay? Because, if it were cosine squared x minus 1, that doesn't equal sine squared x. So just be very careful. This is a Pythagorean identity. 1 minus cosine squared x equals sine squared x. And boom, we just proven it. What's on the left is equal to what's on the right. Let's move on to number 7. Rocking and rolling through these very long notes. Sorry about that. Lots of examples are kind of key with this particular concept when you're starting off. So now we've got secant x minus tangent x sine x equals 1 over secant x. Okay, let's try to rewrite everything in terms of sine and cosine and see if that gets us anywhere. Sometimes it doesn't, right? Sometimes I'll do some, I'll prove or verify, however you want to call it, however you want to say it, and I'm just like, well, that wasn't very good. I don't erase it. I just move on, get another, move on off to the side, and I restart. All right, secant x. I know that that's the reciprocal of cosine, so I'm going to rewrite it as 1 over cosine minus tangent x. I can rewrite that as sine x over cosine x. Sine x is sine x over 1, so times sine x over 1 equals, and then we'll write 1 over secant x. How could I write that in terms of sine or cosine? 1 over secant x is the reciprocal of cosine x. So I'm just going to rewrite it as cosine x. And now let's start. 1 over cosine x. Oh, wait. Yeah. Sorry. Need to make sure I'm doing my fractions right here, right? Now I'm going to multiply first, right? So I make sure here that I multiply sine x over cosine x times sine x over 1, right? Just order of operations. When I do that, I get minus sine squared x over cosine x, right? Because when I multiply fractions, I multiply the top, multiply the bottom, equals cosine x. And in this case, we've already got a common denominator, which is awesome. So I'm just going to rewrite this as 1 minus sine squared x over cosine x equals cosine x. Okay, let's see. So what are we going to do here? Now, let's look at this. 1 minus sine squared x. Could that be a Pythagorean identity? Well, let's look at our Pythagorean identity that we know. We know sine squared x plus cosine squared x equals 1. Could I subtract sine squared x from both sides and get 1 minus? Okay, I sure could. So 1 minus sine squared x over cosine x is the same thing as 1 minus sine squared x. I can rewrite as cosine squared x over cosine x equals cosine x. So this is a Pythagorean identity. So you can rearrange those identities, say, is this the same thing? It sure is. And now we're just simplifying a fraction here, right? We've got 2 cosines up top, 1 on the bottom, basically, right? Cosine x times cosine x. Let me just rewrite that. That's the same thing as cosine x times cosine x over cosine x, right? So these two can cancel, and I'm left with cosine x. So this is just cosine x equals cosine x, and we've proven it. Boom shakalaka. Moving on to number 8. Number 8, ooh, I've got 2 fractions here. What is going on here? Okay, let's see. All right, change to blue. So secant theta over cosine theta minus tangent theta over cotangent theta equals 1. Well, let's just rewrite everything in terms of sine and cosine and see if that gets us anywhere. Secant theta is the reciprocal of cosine, so I'm going to rewrite that as 1 over cosine theta. Over cosine theta is just cosine theta. Minus tangent theta is sine theta over cosine theta. I'm just rewriting what I know, right? Just using basic substitution. Over cotangent theta is cosine over sine. And what we're saying is it's equal to 1. Okay, so now let's start doing this. When we're dividing these fractions, I'm going to multiply by the reciprocal. Keep, change, flip. So let's do this first one first. The first one first. So 1 over cosine theta times, not cosine theta over 1, it's 1 over cosine theta. Minus, let's do the second one over here. That's sine theta over cosine theta. We're going to multiply by the reciprocal. So instead of cosine over sine, we're going to multiply by sine theta over cosine theta. And what we're saying is it's equal to 1, and we need to prove it. So 1, let's do this one first, right? We're multiplying first, right, before we do any kind of subtraction. And I get 1 over cosine squared, right? Does that make sense? Multiply the top, multiply the bottom. Minus, this becomes sine squared theta over cosine squared theta equals 1, right? Doesn't it? Okay. And now what do we got here? Let's change to, what color do I want? Green. So now I'm subtracting these fractions. Do I have a common denominator? I do. So can I combine the numerators? I sure can. 1 minus sine squared theta over cosine squared theta is equal to 1. Well, all right. I see that 1 and I see a sine squared. Well, is that a Pythagorean identity? Because that's really all I would think to do at this point. Let's see, is this a Pythagorean identity? Question mark. I know sine squared theta plus cosine squared theta is equal to 1. I know that because of, we've proven it on the other page, right? Well, let's see. If I subtract sine from both sides, I'm left with cosine squared theta equals 1 minus sine squared theta. Boom, that is a Pythagorean identity. No question anymore. It is 1 minus sine squared theta is the same thing as cosine squared theta. And what we're saying is what's on the left is equal to what's on the right. Anything divided by itself is 1, and boom, we've just proven it. Okay? So all of this work is your answer. It's not just your end result, it's all of this work, the whole process, the logic behind it. So let's get into our very last example, and it's not as scary as you would think. It looks kind of scary, but it's not as scary as you would think. Well, let me see. Cosine squared x minus sine squared x equals 1 minus, well, here I've got this coefficient right here. Let's just think of this as a variable. If that were x, you just have 2 of them, right? So I have 2 sine squared x's. All right, well, can I do this? Plus sine squared x plus sine squared x. Can I basically take one away because they're different signs and be left with cosine squared x equals 1 minus, well, now I've got a negative 1 and plus 1 sine squared x. Well, I'd just be left with, that's like saying negative 2 plus 1, right? I'm just left with -1 minus 1 times sine squared x. So could I like combine them? Sure, they're the same, right? That would be considered a like term. And then now I've got cosine squared x equals 1 minus sine squared x. Okay, I see that 1 in there and a minus, and I've got like a sine squared. Is it a Pythagorean identity? It is. And we've already proven that using 2 other examples, so I'm not going to go through it again. But this is, in fact, a Pythagorean identity. And if you wanted to, you could just add sine squared x to both sides, right? I could add sine squared x to get cosine squared x plus sine squared x equals 1. I could do that, right? Or I could say that 1 minus sine squared x is equal to cosine squared x, all right? So I could rewrite this as cosine squared x equals cosine squared x. But I can end with this fundamental trig identity right here that we know to be true. And I'm going to go ahead and just write that this is a Pythagorean identity, and I can use that in my last and final answer. And that concludes your day 1 notes over verifying trigonometric identities. I know it was long, but I hope it was helpful.